talk about today is a sort of a variant of Newton's method for large-scale optimization. This slightly well, in particular, it's such a variant of an inexact Newton's method. Now, to put that into a context, right, I will primarily focus on this ERM problem, which is the empirical risk minimization problem in machine learning. Now, machine learning is a good context for this for the work that I've done, is because in most cases there are large scales and a bunch of data that you have to work with. Yeah. So, and I will introduce one common ways that usually in the ML community people use to solve it. And next, I'll sort of discuss how does Newton's method or the second order methods fits into these pictures. And I'll sort of describe a couple of challenges of Newton's methods, and I will introduce my own work, how to resolve two of these challenges. Amongst the many challenges, I'll just pick two to resolve, right? And resolve it faithfully. Right, so basically, we are dealing with one optimization problem, that is the unconstrained minimization problem, where you have functions over W and you try to minimize it. Now, the settings, the context is, well, is as follows. So F is sufficiently smooth, probably one of the easiest, well, I mean, the nicest condition you can have, right? Meaning that you have the first order information and the second order information, the gradient and the Hessian. In this case, I'll be assuming that D is particularly large, so large that we only evaluate the gradient and the Hessian when it's necessary, right? Because every time you evaluate that, you're trying to inquire the gradients and the Hessian for that particular point is going to be computationally expensive. For the context, or for the purpose of this talk, I will be assuming F is strongly convex. Now, in the ML background, in the context, it can be formulated as such, right? So we have the finite sum problem, where the finite sum comes from each one of these samples, right? And you have this H, which stands for the model, and then you have L, which is the loss function, right? And together, when you sum each one of them, then you get your finite sum problem, and this is usually called the empirical risk minimization problem. And is, well, in the context of the general optimization problem, this can be formulated as the unconstrained minimization problem. Okay, and in machine learning, as I said before, is particularly large data and large in huge dimension. So there are ways to optimize it. Okay, there are so many methods. There are zeroth order methods, first order methods, second order methods, and higher order methods, and so on. But almost universally, it is solved using the first order methods. Now, in computer vision, it can be seen that the common type of first order method is the stochastic gradient descent with momentum. It's used for the computer vision. The transformers is usually used use ADAM to solve it. The recommendation system is by Adagrad. Okay. Now, it is not without reason why first order method is so popular in the ML context, right, in the ML community. First, it's computationally cheap. So meaning that you just have to evaluate the gradient, which takes one forward propagation and one backwards propagation using the automatic differentiation, right? And it's usually how it's done in the ML. It's conceptually intuitive. The gradient gives you the greatest ascent, and the negative gradient gives you the greatest descent. So as long as you take that step within certain permitted step size, you'll eventually well to get a critical values, right? To either get an in this case it's a global minima under strongly convex. So it's conceptually intuitive and it's easy to implement. Okay, now it's not without its limitation as well. So it is known to be extremely sensitive to hyperparameters tuning. If you have implemented first order methods yourself and you run it on the ML, and you basically take a lot of time to find the correct values for the problem, then you take a lot of time to run iteration by iteration until you get to some optimal points that you desire. It has also the tendency to explode, the gradient exploding and vanishing gradient problems, progressing very slowly at the low gradient region. Well, it is shown that it doesn't really get stuck in a saddle point, but when you have a very low gradient region, it will progress very slowly. It's painfully slowly. So generally, it has slow convergence, right? So basically, we have the first order method is do all the heavy lifting in ML. Now, one might ask, why not, right? So for example, if you don't have gradient, then you might resort to zeroth order methods, right? For example, you don't have gradient, the gradient is expensive or it's private for some reason, you can't simply access to it. Then you might resort to zeroth order methods. If you have gradient, then generally you can exploit the first order information to get a faster descent. Now, following this logic, following this reasoning, if you have second order methods, then why not just proceed one step further, right? And you utilize the second order information in your problem. So what about the second order methods? So just one very basic example of second order methods is called the Dan-Newton's method. What you do is you choose any starting point. At each iteration, then you compute the Newton stats, right? So S equals to the inverse Hessian times the gradient, negative of that. Then what you do is before you step into the next iteration, you compute the step size such that it satisfies some condition. So that is the descent condition, right? So the next step, sorry, this should be K. So the next step should be the next step, the function value at your next step should be somewhat lower than your current iterates, right? And it's not just lower, it has to be lower by certain margin. So this term here is negative, okay? So it has to be lower by certain margin. And if it satisfies this condition, you take that step and you proceed to the next step and you repeat, right? You rinse and repeat. So this particular method is convergent. You can start any point and it will converge to an optimal point. So what benefit does it offer? First, it's very robust to hyperparameter tuning, meaning that for any hyperparameters, there's a wide range of sort of acceptable parameters that you can put. You don't really have to painstakingly look for the right amounts of the parameters. Generally, is pretty good. It has because you're utilizing the Hessian, it's known to escape low gradient region very well. Generally, it has fast convergence rate. If your starting point is close to the optimal point, it even has a quadratic convergence. It sometimes argue that it has a better generalization performance. So for the fourth trait there is it pertains to the ML community, right? Whether or not it generalizes well. And some argue that it might generalize well better than the first order methods. Now, well, then I think that's the end of story. Let's apply Newton's method to on every ML problem, right? So what are we waiting for? Then we just do it. We solve the world's problem. Well, unfortunately, that's not the case. So just have to hold your horses. It's not as simple as that. So if you just go on Google and just type why Newton is not used in ML, it's not without its own reason. Now here is well, here's the discussion from the Stack Exchange, right? One reason for that, and it's the primary reason, is because the function in ML is this. You have huge sample, as I said before, and you have a very huge model. This is an extremely large model. For example, I just looked up yesterday for ChatGPT, it hits like nearly 100 billion parameters. So for the Hessian, it's a 100 billion by 100 billion matrix that you have to deal with. And I'm not sure how you would probably do that. It's just simply not feasible if you're trying to handle that kind of large matrix itself, right? And also, the function is not convex. It's not strongly convex. Most of the problems in ML, they are non-convex. So, and here are the summarized problem, the challenges of the second order methods. Okay, well, Newton's method is too complicated to implement. This is sometimes I hear it, but it's probably not so important. But the non-convexity is very crucial because non-convexity, well, may lead to singular Hessian. That means that you don't have an inverse of the Hessian. That is not well defined. Newton's step is simply not well defined. And if it is well defined, it may converge to a saddle point. Just if you just naively implement it, if you just naively run it. Storing Hessian is too expensive. If you have that large of a matrix, it's simply storing it is very expensive. When n is huge, right? In terms of a finite sum problem, evaluating that particular expression there to the second order is again very expensive. Inverting it is almost practically impossible. Now, these are the complaints. And also, I will just add one more thing. Newton's method is actually quite slow, and I will argue why that is the case. Now, for the purpose of my talk, I will be dealing these three particular points. Okay, how you can deal with the storing the Hessians being too expensive problems, and inverting the Hessian is impossible problems, and what do I mean by Newton's method is actually quite slow. Okay, so let's take a look at the first 2 points, the storing Hessians and the D being very large, which computing the Hessian, the inverse of the Hessian is practically impossible. So one common solution to that, okay, so when storing Hessian is too expensive, well, I mean, if you actually implement it before, you know that you don't actually need the whole Hessian itself. You only need the Hessian vector product. Okay, so no matrix to store. Okay, so that's one thing. And the second thing is the computing the inverse of the Hessian is almost practically impossible. Well, in that case, we don't compute the exact inverse. We approximate it, right? And we approximate it with some measures of approximation. So we use inexact Newton step instead of exact Newton step. And there are iterative methods to do that. And there are iterative methods that only require matrix vector product, meaning the Hessian vector product. Instead of assessing the whole Hessian, you treat the Hessian as an operator and take in a vector and you just compute another vector, okay, using the Hessian as an operator. Examples include Jacobi's methods, conjugate gradient, conjugate residual, and minimal residual, right? So this is one example that utilizes these iterative solvers called the truncated or inexact Newton's method. So again, you start any point, right? But instead of doing the inverse of the Hessian, you do the inexact Hessian, okay? By some measures, right? So in this, what commonly used measures is the relative residual measures. So where you have the residual and you're trying to compute S that is some degree smaller than, times the norm of the gradient. And you do exactly the same thing and you rinse and repeat. Okay, so, and it turns out that this is also convergent at starting at any point, which is good. Okay, so meaning that we can now actually run Newton's method on the very large scale problem. So in this particular example, I set my theta to be 10 to the negative 7th, close to the exact Newtons, to the Newton steps, and where the dimension is about 3 million. Now imagine if you sort of compute the exact inverse of the Hessian, you do Cholesky, or if you do QR with 3 millions by 3 millions matrix, it simply is almost impossible. It's practically impossible. So, and with the inexact Hessian, you can solve the problem now. Okay. Now, depends on what iterative solver you use. It's named differently, right? In this case, I use conjugate residual as an iterative solvers, so that is why it is named as Newton CR. Now the dotted line is the gradient descent with line search. However, there is a but behind the pictures, the plot. Inexact Newton's method actually can still be quite slow. So that one, so just keep in mind, this is function value versus iteration. So if I look at this, the same plot from the other perspective, is the oracle calls versus versus the function values, or the time versus the function value. the result is clear as day. So you can immediately see that Newton's method is still being beaten by the simple line search, gradient with line search, gradient descent with line search. Now, just let's do a quick recap of what an oracle call is. So an oracle call is just a way to characterize how costly or how the computational cost of a function call. So one oracle call is equivalent to one function value evaluation. And two oracle call is required to evaluate gradient because you need one forward propagation and one backward propagation. That requires two oracle calls. And in addition to the gradient, you also need another two oracle calls to compute the Hessian vector product. So if you calculate that way, and you sort of compute it, and then you do a function value versus the oracle call plots, and you realize that Newton's method is still very expensive to compute. Okay, as you can see clearly in these pictures, that line search is much better. That is the things that I'm trying to improve on. So that is just one issue. The other issue is this. Now, one may ask that surely, right? In terms of iteration, Newton's method must be faster than gradient method. Well, yeah. So the time cost, the time spent, the oracle call cost, they are all maybe very expensive. But in terms of iteration, surely Newton's method must be winning. Now, I argue otherwise. It's actually not true. Empirically, yes, if you actually implement it, almost always you will see Newton's method in terms of iteration, it beats gradient descent with line search. But theoretically or analytically or in terms of worst case convergence, it is not the case. Okay. Now, just a couple of quotes from other people. So by Coralia Curtis, one of her new book. So she said that indeed many second order methods actually do not converge faster in the worst case than first order ones. And worse still, under strongly convex problem, the nicest problem you can possibly have in the nonlinear case, there are many people has already noted, even under strongly convex setting, the worst case complexity of an inexact or the Newton's method actually it's actually worse than the worst case complexity of the GD with line search. Now I will explicate that. I will spend a little bit more time to answer, well, to sort of see why they are saying that. Now, before we do that, I need to introduce a notion of called condition numbers. So characterizing the conditions of a function. So the condition of a matrix can be characterized as such, right? So the largest eigenvalues divided by the smallest eigenvalues. Now, if you consider the Hessian, all the Hessians in your function, and you sort of try to upper bound this, right? And this will give you the condition numbers of the problem itself or the function itself, okay? So this is what I term as kappa. Now, intuitively or pictorially, this is what it looks like. So for ill condition problem, meaning you have large condition numbers, you can sort of see in terms of quadratic problems, right? You can see it's very skewed. It has, well, it's pretty skewed, okay? In terms of well-conditioned problem or small kappa, you sort of get a very circular contours for the quadratic problem. So that's basically how we characterize it. And for many functions, you can characterize the similar way. Now, under gradient Lipschitz and strong convexity assumption, this is the worst case complexity for the gradient descent with line search. So what it says is that for every iteration you take, right, it is certain ratio smaller than, well, smaller than this particular constant here. Okay, so this is smaller than 1, and which is what we want, right? Because the more you iterate it, so you keep multiplying it, and the terms will get smaller and smaller, which eventually you will guarantee to hit the F star here. Now that depends on kappa. Okay, so the bigger the kappa, the worse the worse it is. Okay, so now let's take a look at the Newton's method. So this is again gradient under the assumption of gradient Lipschitz and strong convexity assumption. You have a kappa squared. Now apparently I've looked up online. I'm not sure how you would improve upon that. Okay, is kappa square is worse than the gradient descent. It depends square as compared to the gradient descent. So in this sense, Newton's method is slower than the gradient's method. Okay, so let's just do a quick recap, the overview of the challenges that I just described. First thing first, the computational cost of inexact Newtons may be too costly. Now, that is true for the operation call, the operation call or the oracle calls and the time span, okay? The reason for that is simply because we spend too much time in the inner solvers, okay? We're trying to solve the Newton system or the linear system to that particular accuracy before we take that step to the next step for the Newton's method. So we simply spend too much time and computation in the subproblems. And on the other hand is we're not knowing what the optimal inexactness is. If you set it too small, you spend too much time. If you set the inexactness too large, which means that it close to 1, you might not utilize the Hessian well, right? You underutilize it. Okay, yeah. So the second problem that I mentioned is the worst case iteration complexity of Newton's method is worse than gradient descent. So that is just repeating the same problem. So Newton's depends on kappa square, while gradient depends on kappa. Okay, so how do we solve this problem? Now that is to proceed to resolve these two problems. I propose this, right? This is sort of the one perspective to look at this problem. The reason why that is the case is because there are two levels problems here. Now, this is the truncated Newton stats slides from the previous slides ago, meaning that we have this two-level perspective. We have Newton's perspective, and then we have the subproblem's perspective, right? So what Newton's require is that Newton's wants the Newton stats or inexact Newton stats, and then it passes the problem to the subproblem solvers, the CR problems. That is CR problem, and CR just focus on solving that until it hits that certain requirement, and then CR will say, well, there you go, this is your inexact Newton stat, and go on and use it. So because you separate these two problems as if they are two independent problems, so you have this problem. Okay, so the proposed solution is to integrate the outer solvers, which is Newton's method, and the inner solvers. In this case, I'll be using the CR solvers, right? Integrate together, let them communicate. Okay, so bridging the inner outer solvers. So this is my proposed solution. So these problems are not solved in isolation. You don't solve one problem and then another and then come back and forth. But you solve this together, well, which we'll see later. So these two problem solvers communicate via something what I call the sufficient descent condition. So by introducing this condition, you allow Newton's method to exploit the properties of the inner solvers. In this case, it's the CR solvers. Okay, so again, so let's just quickly, because the numerical linear algebra side of it is crucial for this for my work. So I will just take a few minutes to look at this one particular subproblem solvers, the linear system solvers, the conjugate residual. So the conjugate residual is just like conjugate gradient, which is very popular. It's not exactly, but it's very similar to the conjugate gradient. And if you can recognize it, you'll realize that it has an additional H or the additional matrix in every times you sort of try to multiply, try to form the coefficient or the constants, right? So for the conjugate gradient, you simply have RR, but for the conjugate residual, you have RHR. Okay, that's it. That is the difference. Now, with conjugate residual, it comes with a lot of nice property. This particular property, the first one, is the property that is crucial to sort of proving the faithful Newton's method, right? What it says is this: for every time you iterate within the CR solvers, the gradient and the angles between the gradient and the inexact Newton stats gets larger and larger. It's not exactly the gradient, but it's sort of the magnitude of it, right? So it gets more negative and negative, meaning that this inexact newtons, if you iterate more within the CR, it gets more and more closer to the Newton step. Now, in addition to that, we also have the norm of the Newton steps getting monotonically larger, and the residual is also getting monotonically smaller. Okay, so these are the three properties, and there are many more of CR properties that are useful in optimization, but these are the three that stands out the most. Okay, so for the inexact newtons, this is what you do, right? So the not terminated part, you change it with the relative residual. You iterate until it hits this, and then you terminate. Okay, so the problem with this, okay, let me just provide a little bit insight to this. Maybe, yeah, okay, let's just do that. Okay, so imagine that you have two inexactness parameters, right? So you solve it very close to the Newton's step, and the other one you solve it roughly. So this is what you get in terms of iteration, and this is what you should expect. The closer you solve to the Newton step, the better it is, okay? And then the less iteration it takes to converge. But in terms of time and oracle calls, right? Because you have a smaller inexactness, that means that you need to spend more time in CR to solve for the Newton step. Okay, so naturally you would expect it takes more time for the smaller value to converge, and more oracle calls for the smaller value to converge, and which is true. Okay, so let's just skip that. Okay, so we have sort of the conundrum between the two, right? For small theta, s is closer to Newton steps, right? Large is s is closer to the gradient steps. Greater descent and less descent, and possibly oversolve for h, right? If you keep solving it, you don't really gain much after a certain point. For the right hand side, if you have large theta, you possibly underutilize h, and more computational costs, less computational costs, and so on. Now, the right question to ask here is, at any given outer iteration k and any inner iteration t, now you have the oracle call. Should you spend this oracle call in the inner solvers or the outer solvers, right? In the inner solvers, meaning that you're trying to gain more accuracy in Newton steps. If you spend it on the outer solvers, meaning that you're trying to take it to the next step and to get to the next iterate, right? So that will be the ultimate question to answer. So, well, introducing sufficient descent condition. This will, arguably solve the problem. So this is how I define it. So S is called row sufficient if and only if that thing hold. Okay, that is just this is the Armin-Hole line search condition. Basically, it's the line search condition. So if S satisfied this, we call S row sufficient. Okay, so that row is the curvatures parameters here. Then it depends on big or small, depends on how much you want it to descend. Now, use this in CR, okay? So instead of using the relative residual as your termination condition, but just simply replace the not terminated condition as ST is not row sufficient. Okay, so this is what it says. So at the first iteration, you iterate, right? And once you get after you iterate the first iteration, you get S1. Now you ask the question whether or not S1 is row sufficient. If it is, that means that it produces a good descent. Then it means it's worthwhile to go to the next step. To go to the next iterates within the CR solvers. Okay, so you go to S2, and you go to S3 all the way until you hit some ST, where ST is not row sufficient anymore. That means that there is no point to go further within the CR solvers anymore, and you retreat back to the previous iterate, and you use that. You know that it was sufficient, so if you use that directly, it will give you descent. Okay, so that's basically the idea. So for t greater than 1, if you keep iterating, if you hit the ST being not rho sufficient, then you can retreat back and return that st minus 1 as your update direction. Now, if st equals to 1, meaning that for the very first iterate, you already hit st as 1 being not rho sufficient, then you use that as a gradient step and you retreat back to the backtracking line search. Okay, that will be just the common backtracking line search that we're all familiar with. Now, that is the faithful Newton. So we call it the faithful Newton CR, conjugate residual with line search, because in the worst case scenario, where every iterate is not rho sufficient, then you still have to take the backtracking line search, right? So that is the worst case. But empirically, that case is almost not happening when you actually run in the in real life example. So this is FNCR. So the termination condition no longer is the relative residual, but it is the sufficient descent condition. That particular sufficient descent condition provides a direct communication between the outer solvers, Newton's method, and the inner solvers, the CR. So it saves a bunch of oracle calls. You don't spend unnecessary oracle calls within the inner solvers anymore. At least that is the idea. Okay, now, of course, that is the preliminary version. There are a bunch of sort of safe mechanism that you have to put in place. I wouldn't bore you with that, but basically the general idea is what I have just introduced to you. Okay, now what about the convergence rate? Okay, so to obtain a better convergence rate, I changed my assumption to Hessian-Lipschitz. Okay, so under Hessian-Lipschitz and strong convexity assumption, faithful Newton CR attains a global superlinear convergence. So meaning that you start at any point, you will attain a superlinear convergence. Okay. Now, there's one little side note there. This particular superlinear convergence rate is not actually only FNCR-LS can attain. It's actually a more generalized case. Because FNCR-LS is actually a generalized version of the inexact Newton's method. So for particular settings of certain hyperparameters, the FNCR-LS will reduce to inexact Newtons or even the exact Newtons. It depends on how you set the parameters. So meaning that this particular theorem actually applies to the inexact Newtons. Okay, so the inexact Newton's method also achieves a global superlinear convergence under this particular setting. Okay, so here are the few experiments. Now, as you might say, it gains a little bit of age. Okay, now across all the problems, it almost does. So as we can see, the solid blue lines and the dashed blue lines, in terms of oracle calls, it's actually achieved quite a good convergence and quite a fast convergence as well in terms of time as well. I mean, yeah, probably you can't see it very much. But I will just put up this particular example. This, I think we have almost again 3.5 million dimension for this problem. And next, so this is the other interesting plot, and I would like to show you. So FNCR compared with the accelerated method, right? So this accelerated method, this is general convex problem, meaning that the smallest eigenvalues of the Hessian it can be 0. For the general convex problem, so the blue line and the dashed blue line, they are FNCR, and the rest this is the accelerated cubic regularization Newton's method. This is the normal cubic regularization Newton's method. This is gradient descent, which is this line here. And the other two is also an optimal a tensor method. Okay, this is what they promoted. And in their paper, they obtain the optimal convergence rate. This is the best rate you can get in the convex problem. Now, that is the iteration. But what I'm showing you here is just to prove a point. The Oracle core, in terms of Oracle core, is actually still very these methods here, the accelerated methods here are still quite expensive. Yeah, I think that is the end of my talk.